The microscopic world of chemistry is a chaotic marketplace. Almost every element is constantly seeking out partners, bonding or exploding to achieve atomic stability. On the far right of the periodic table sits a group of elements that ignore the chaos. These are the noble gases. Their official name is debated. IUPAC designates transition metals as Group 8, but conventionally that title is held by these invisible gases. This inert group consists of exactly 6 elements: helium and neon, argon and krypton, xenon and radon. These are the laziest elements in the universe. But our modern world, from high-intensity lasers to life-saving medical treatments, is completely dependent on a group of gases that seemingly do absolutely nothing. At the atomic level, this is dictated by a full valence electron shell, usually containing exactly 8 electrons. While other elements scramble to swap or steal electrons, noble gases are already chemically complete. They have zero motivation to interact. Helium is the single exception, possessing only 2 valence electrons. However, because its single shell is full at 2, it maintains that same perfect stability. This refusal to react allows these gases to function as a perfect, invisible shield. Inside a light bulb, for instance, we use argon to surround the tungsten filament. It physically prevents oxygen from reaching the hot metal, which would otherwise be destroyed by oxidation. Argon also serves as a neutral carrier gas in chromatography, allowing scientists to move samples through analysis without the gas interfering with the chemical results. In deep sea diving, helium acts as a life-saving shield. It is mixed with oxygen specifically to prevent the toxic effects other gases can have under the immense pressure of the deep ocean. Helium's extremely low density also provides immense lifting power. It allows colossal structures like the USS Akron airship to float without the risk of combustion found in more reactive gases. That same safety and lift made mass entertainment possible on a grand scale, allowing massive inflatable parade characters to float safely above crowded city streets. The primary value of the noble gases is defensive. They are used to physically separate and protect reactive materials from destroying each other. Shielding is one application. We can also force massive amounts of electrical energy into these gases. Because they physically refuse to bond, these atoms absorb the energy and expel it as intense, vibrant light. Neon is the primary example, producing the bright, ubiquitous colors used for commercial lighting and signage around the globe. Heavier gases, krypton and xenon, are utilized when we need to handle higher intensities of energy. Krypton powers high-efficiency lamps that pierce the night and is a core component in high-powered lasers. Xenon is harnessed for instantaneous, blinding bursts of light, which are used in everything from car headlights to specialized camera flashes. At the very bottom of the periodic group sits the extreme outlier, radon. While it possesses a stable electron shell, its nucleus is so massive that it physically falls apart, creating a dangerous radioactive gas. This radioactive instability is the only active trait in the group. We harness it for targeted cancer treatments and advanced scientific research. The history of these gases tracks a movement from chemical obscurity toward industrial necessity. Scientists once viewed these elements as chemical dead ends, labeling them Group 0 because they appeared to have zero valency or practical use. Modern engineering relies on this absolute lack of reactivity as a highly specific, irreplaceable tool. In a physical universe defined by constant, chaotic chemical change, an anchor of perfect stability is a rare and valuable resource. The noble gases show that a state of total inaction can be as transformative as any chemical explosion.